Good morning from the UK, or good afternoon or good evening if you're joining us from another time zone. Welcome to today's webinar on reducing risk via a COTS-based certifiable avionics platform. I'm Mark Tootle and I'll be your host for today, and I'm joined by Gabby Davenport from Intel, Greg Sickens from Curtiss-Wright, and Joe Richmond-Knight from here at SYSGO. Gabby will be introducing Intel's DAL A certifiable processors. Gregory will then show how Curtiss-Wright take these and turn them into a DAL A certifiable hardware platform. Joe will be talking about the SYSGO high safety certifiable RTOS and Hypervisor, and ultimately how these technologies align to reduce risk in a COTS-based certifiable avionics platform. Please ask any questions you have via the chat during the webinar, and we will try to answer them at the end. If we can't accommodate all of the questions, we will answer them offline after the webinar. So now I'd like to hand over to Gabby. Gabby, over to you.
Thanks, Mark, for the introduction. My name is Gabby, and I am a product marketing engineer for Intel focused on the federal and aerospace business. Today I will discuss Intel's offerings to assist with the certification of COTS parts. Intel Corporation is a multinational technology company that has a strong global presence. We have operations and customers in numerous countries. This global reach allows us to tap into diverse markets and collaborate with partners worldwide. Intel has a long history of innovation in the semiconductor industry. Our research and development has led to significant advancements in microprocessor technology and manufacturing processes. Compute systems are becoming larger parts of aviation, and Intel processors deliver significant advantages for avionics. Intel's processors have been built for industrial use conditions. These use conditions include long life of parts, 7 to 15 years for some parts, support for extended temperature range, and high performance in a single package. This offers aviation customers processors that are flexible in size and weight packages. Furthermore, Intel's processors offer great performance for a lower core count, as a higher number of cores can increase complexities. Intel has long supported customers as they pursue safety certifications in the industrial and automotive markets. It has been a natural extension for Intel to help customers meet the safety requirements and certifications for the aviation market. Intel hired an FAA DER to look at the industrial and automotive standards seen on the slide and the standards for 178/254 to compare them for similarities. The results of the analysis are shown in the table. The standards are similar with the exception of DAL A, which is one step higher than the industrial standards. We leveraged the data that we are building for the automotive and industrial domains and augmented that data to develop offerings that assist with avionics certifications. This provides the data that you would need to integrate into your certification packages based on the selected processor. Within our core processor family, Intel offers SKUs that are targeted to meet the needs of avionics customers. Our Intel 11th generation Core i7 1186 GRE and 13th generation Core i7 1376 PRE are special parts with thermal throttling disabled. This means that the chip will not dial back performance to prevent itself from overheating. This allows for improved determinism, as performance is not affected and customers can choose how they want to manage temperature concerns. Our Core i7 1186 GRE is a 4-core processor, and our Core i7 1376 PRE, which will be featured in today's presentation, is a hybrid architecture comprised of 6 performance cores and 8 efficient cores. The efficient cores of the Core i7 1376 PRE can be configured for dual-core lockstep. Dual-core lockstep is a redundancy technique that can improve reliability and enhance fault tolerance. This can be useful in high reliability computing and satisfying the requirements of safety-critical applications. Both of these parts support Intel Iris Xe graphics. Additionally, these parts have an Airworthiness Evidence Package available for purchase. The Airworthiness Evidence Package, which we refer to as the AEP, accelerates time to certification by providing access to data that is normally not offered to customers. Once an NDA is signed and a license is purchased, customers can access this data to assist in developing their certifiable systems. The AEP includes items such as failure modes, effects, and diagnostic analysis, reliability data, product certifications, sighting reports on the processor, and field failure reports with the root cause so customers can see what is happening with the parts. Extra analysis is provided for single event effect data as well as other areas of interest to avionics customers. The AEP also includes our AMC 20-193 guide, which provides guidance on how to configure the parts to limit the interference between the cores. This guide also helps to achieve the most predictable performance out of the parts. The AEP enables customers to build their certification packages on the whole software stack, which all layer up to provide the foundation for your applications and ultimately build a complete end-to-end certifiable system. We currently offer DAL A and DAL C versions of the AEP. Intel real-time technology supports new solutions that require a high degree of coordination both within and across devices. Intel time-coordinated computing enabled processors deliver optimal compute and time performance for real-time applications. Pair these processors with Intel Ethernet controllers featuring IEEE 802.1 time-sensitive networking support, or with any number of other popular networking devices to power complex real-time systems. Essentially, we enable real-time resource management, which is key for multiple systems working together in an aircraft. Intel real-time computing performance and solutions are focused on hard real-time use cases where missing a deadline is a system failure. Hard real-time is necessary in areas such as robotics, automotive, and utilities where a capability fails if it cannot be executed within the allotted time span. Real-time offerings from Intel support new solutions that deliver both high compute and real-time performance by prioritizing real-time workloads access to cache, memory, and networking, minimizing disruption from other workloads, optimizing performance for both real-time and non-real-time workloads, as well as ensuring availability in both native and virtualized environments. Intel time-coordinated computing time synchronization provides a hardware mechanism to coordinate the various clocks found in individual IP blocks. Intel time-coordinated computing timeliness provides a hardware mechanism to specify latency of data packets from one functional block to another. Time-sensitive networking provides bounded maximum latency for scheduled traffic through switched Ethernet networks. Time-sensitive networking is a set of IEEE 802 standards that are defined by the IEEE Time-Sensitive Networking Task Group. These standards enable ultra-reliable and low-latency communication over Ethernet to support time-sensitive applications. Time-sensitive networking achieves this by using time synchronization and traffic scheduling. I'll now hand it over to Greg, who will be speaking on behalf of Curtiss-Wright.
Thank you, Gabby. This is Gregory Sickens, and I'm with Curtiss-Wright, and I'm going to talk about the next level up on the platform stack, where we take the safety-certifiable COTS processor from Intel and we move up to a safety-certifiable board-level product ready for software. First of all, just for those out there who are not familiar with Curtiss-Wright, just a brief introduction. So we're a diversified international provider of highly engineered products and services, primarily focused on the aerospace and defense market. We've got a long history of innovation. We've been listed on the New York Stock Exchange back in 1929, so we have a long history of a stable and growing company that you can rely on and trust for your solutions. So briefly, why the Safety-certifiable COTS Intel processor? So we've selected the 13th generation Core i7 1376 PRE, formerly known as Raptor Lake, as the processor of choice for our next generation Safety-certifiable processing board. It's selected because it provides the highest performance available with safety cert support, that is through the Intel Avionics Evidence Package. It includes a performant integrated Intel graphics processor, which is in line with the high performance GPUs that our customers have been using. So you're not losing any graphics performance here whatsoever. It also provides all the interfaces and then some that we would need to support a SOSA I/O intensive profile product. And what that means is SOSA defines I/O pin out, which then get published into VITA 65. We won't get into that detail, but essentially what it does is it defines what each and every pin going between the card and the backplane do, so that it is multi-vendor interoperable, if you will. So back to the Intel processor. This processor that we've selected is a hybrid architecture which provides benefits in terms of improved determinism and real-time response, as well as efficiencies within the operating system can be increased and thereby reducing power consumption. And you can fine-tune the overall system performance, moving application aspects between the big cores and the little cores. So you can see the V3-1222 module on the right-hand side. It is a fully conduction-cooled and ruggedized module that can handle the harshest environments that can be thrown at it. With safety-certifiable COTS, we avoid adding hardware costs and limit the versatility offered by the Intel processor that would come with custom hardware solutions. That is, we provide a wide suite of I/O capabilities with this product so that it can meet many different system needs. And by having a single board solution, single board configuration that can be used in many different systems, we build up a larger database of history and less likelihood of any latent defects, right? So it lowers the probability of latent defects that you might get if you have a custom dedicated hardware solution developed specifically for your system. So this would have a larger pedigree associated with it. So safety-certifiable COTS, it reduces your risk and schedule in that it's developed in alignment with applicable airworthiness regulations for airborne electronic hardware. That is, we work to AMC 20-152A as it applies to design assurance and level A with respect to process. We work with an FAA accredited DR as our auditor for our process and for our development as we move the products through development to completion. So this has a level of independence and inspection to basically provide the best assurance we can without a program of record that the product will meet the objectives of AMC 20-152A. Just a little comparison between the traditional approach and the safety-certifiable COTS approach. So with the traditional approach, the requirements are flowed down from the aircraft need to the system, and then from the system to the various modules, the boards that would need to be developed to implement the system. So that involves a schedule for development, so the product is not available immediately, that's specifically safety-certifiable configuration, as well as costs in that you've got custom developed hardware for each program that may need that function or a board. This is tailored for the application, so all the data generated at the board level does specifically tie back in and trace to the system need. With safety-certifiable COTS, it's a little bit different, obviously, in that the hardware requirements are flowed up to the system integrator, who would then do the traceability of system requirements to the board level hardware requirements, therefore completing the traceability chain. This reduces project cost, schedule, and risk in that what we have here is a catalog list price product, so there's no surprises later if it costs more to do a cert or whatever. The cert artifacts are complete. they've been reviewed, they're in configuration management, and they're ready to deliver. There's no risk of something coming out and hitting you later for additional schedule and money. So there's no development, no waiting. The boards are once we've developed the product, the underlying product, all the data for that product and the manufacturing of that product is all under configuration management control, and we can just turn the crank and build the product as you order. It's also used, as mentioned earlier, used in multiple applications, minimizing risk of latent design errors, and then the system integrator puts in the context of their specific system need, and we provide the additional data needed to do that. And we also provide tables in the plan for hardware aspects of certification, which specifically go through each objective of the AMC 20-152A and the AC 20-193A for multi-core, and the AC 189 one for management of problem reports. And so we go through all of that, and so it's a clear picture of what we do at the board level and where the system would need to fill some gaps. And again, that depends on the application use of the hardware. So things we provide, we make it easy to tailor so that you can address how the system is using the hardware and get the real results for your specific use of the V3-1222. Now we'll go through a couple of examples. So these are simplified examples. This one here is for sensor processing. So we're showing 3 V3-1222s with the Intel processor, 64 gigs of memory. Each one can connect to up to 4 sensors of 1 gigabit Ethernet with TSN capability. And they can communicate with each other over 10 gigabit Ethernet, such that it doesn't matter whether the sensor's on the third processor, that sensor data can be shared across to any of the other 2 V3-1222s. So that's a way to get up to 12 sensors into the card, do some processing, it can be shared across the cards, and so on. Let's say you want to look at the sensor data, you want a visual interface, you can have up to 2 displays connected through using DisplayPort interfaces. That is, every 1222 supports 2 display ports, so you can actually have additional ones across the other 2 V3-1222s. So the system could do up to 6 display ports if you so desired. Also showing on the extreme right, there are 2 USB interfaces for keyboard and mouse. So if you know the specific model of the keyboard and mouse, you can specifically tailor the software stack to just those items, and therefore you have something that can be reasonably safety certified from a software perspective for DO-178C. The hardware is supporting the USB interfaces from the board level. So that's one example. Now, completely on the other opposite end of the range of the example, we're looking at something that's more graphics and video processing oriented. So showing the V3-1222 in the middle, it's connected to a V3-1222 on the left through PCIe. I call that one Fabric. So this is the PCIe interface as defined by the SOSA implementation. And then on the right hand side, we've got a second PCIe interface. So every V3-1222 has 2 PCI Express interfaces that are completely separate. So there's no interference channels between these 2 interfaces external to the Intel processor. We call this one a dedicated one, and what we're really targeting here is for it to be used with a external FPGA card if you needed to do video capture or drive additional displays. So that allows the FPGA direct access into the V3-1222 system memory, which in case of video capture, the GPU can pick up and render that into frames. And you can also have a display controller implementation FPGA to provide ARINC 818 or more display port interfaces that can look at the system memory where the GPU is rendering frame buffers to, and you can pick up those frame buffers and drive additional displays. So it's a fairly unique configuration of the V3-1222. And that completes my overview of why we selected the Intel processor. It's the most performant one with safety cert support. We put it on a board. We support it with safety-certifiable COTS, so that it completely aligned with the FAA and EASA, and also that for the defense market space for safety, meeting their safety cert objectives, and providing that as a COTS solution that with all the additional data that would be needed to support a system integrator to tailor that to their and put it into the context of their specific system needs. This also has advantages, of course, if you have multiple systems that need a processor board, but the system requirements may be subtly different, and that you can have a common hardware solution across those systems, as opposed to having custom boards used in each system, for example, which would be a worst case example. So there we go. Now we're at the safety certifiable board level, ready for system integration, which would then be where software would be attached to it. And that's where Joe from SYSGO will take over and talk about the software solution from SYSGO to complete this stack.
Thank you, Gregory. Okay, now we move on to SYSGO. My name is Joe Richmond Knight, and I'm a Field Applications Engineer for SYSGO. I'd like to spend some time now providing you with an introduction to who we are, what we do, and what we specialize in, with a focus on demonstrating how we support software development for high DAL applications. SYSGO is the leading European operating systems vendor for embedded systems, providing safe and secure technologies and services through our products like PikeOS, a hard real-time operating system and hypervisor, and the Linos, an industrial Linux distribution. More on these later. Founded in 1991, we have been around for a while and know our customers' needs and challenges, especially when it comes to the certification of high-integrity systems, focusing on safety and security. Finally, since 2012, we've been part of the Thales Group, enabling us to maintain our European technology status with no export restrictions like ITAR. At SYSGO, we have three main products, complemented by additional resources to support your project. Firstly, PikeOS is a real-time operating system and Type 1 hypervisor, capable of achieving the highest levels of certification for both safety and security on all major MMU-based platforms. In fact, PikeOS has been designed from the start for avionics and DAL A certification based on prior project experience and through the use of technologies like ARINC 653. The unique combination of real-time operating system and hypervisor means PikeOS can host deterministic applications alongside general-purpose guest operating systems whilst maintaining separation in both time and resource. We also have a variant of PikeOS which targets processors with a memory protection unit only, called PikeOS for MPU. Our third product is an industrial-grade Linux distribution called Linos, which can operate as a standalone Linux OS in its own right, or be used as a guest operating system on top of PikeOS. Finally, we offer supplementary products and services to support our customers, namely board support package development services, certification evidence kits for both our off-the-shelf products as well as BSPs, and other professional services like training and systems architecture consulting, known as SysArch. PikeOS is our flagship product, which combines an RTOS and a Type 1 hypervisor into a single, highly portable operating system. It supports multiple guest environments called personalities, including POSIX, ARINC 653, Linux, including our own embedded Linux distribution called Linos, Android, PikeOS native, and many more. Various applications can sit on top of PikeOS with mixed levels of criticality, which is achieved through our separation kernel architecture, supporting most popular platforms including x86, ARM, and PowerPC, to name a few. PikeOS is fully built in Europe and therefore has no export limitations. Finally, PikeOS is fully certifiable to the highest safety and security standards, including DO 178C DAL A and Common Criteria EAL5+. PikeOS provides a modular certifiable framework. This includes the PikeOS microkernel and the PikeOS system software, which runs in user space and is responsible for initializing the various partitions as well as starting the system. The microkernel, PSSW, and architecture support package are available as certifiable components. The platform support package is usually certified in the context of the project. We also have certifiable APIs available for a number of personalities, including POSIX and PikeOS native, as well as certifiable add-ons which extend the functionality of PikeOS. The certifiable file system provides a fail-safe file system with more functionality than the ROM-FS included in PikeOS. It includes the basic file operations expected by an embedded file system, as well as being able to handle directories and file manipulations. It's still a simpler file system compared to standard Linux, but this is intentional as it's designed for certification. The certifiable IP stack provides a safety-focused UDP-based network stack for PikeOS native and POSIX environments, including features like IPv4, ARP, and ICMP to name a few. Finally, the certifiable maths library is designed to allow the safe execution of common mathematical functions alongside the FPU on board the platform. In the case of DO178C for civil avionics, software can't be certified in isolation, so must be certified as a full hardware and software system. Therefore, we provide certification kits, including the necessary artifacts and documentation, as well as support, to fulfill the wider system certification requirement. PikeOS has been certified up to DAL A for civil avionics, as well as the highest levels in many other vertical market safety standards. This high pedigree in the safety critical domain is complemented by equally high cybersecurity credentials in our common criteria EAL5+ achievement for the PikeOS separation kernel. PikeOS is especially well suited to support modern multi-core Intel processors, allowing maximum utilization of these chipsets in systems that are constrained by size, weight, and power. PikeOS is especially well suited to support the modern multi-core Intel processors, allowing maximum utilization of these chipsets in systems that are constrained by size, weight, and power. PikeOS has a number of capabilities aligned with the AMC 2193 guidance on the use of multi-core processors in safety-critical avionics systems, which we'll touch on further later. Finally, SYSGO has a rich heritage, with over 75% of our engineering team having prior experience in safety-critical software, so it's a topic our team understands well, allowing us to build certification kits and provide support in your product certification journey. Okay, let's briefly run through the various application development environments supported by PikeOS. As I touched on earlier, we call these various application development environments personalities, based on a combination of well-known APIs and popular programming languages for safety and security. First, we start with PikeOS Native. Native provides a minimal C environment to facilitate the development of high criticality applications, as well as an API to access OS services like IPC. Regarding the support of ARINC 653, a popular avionics standard, PikeOS itself implements the majority of the ARINC 653 functionality, for example, health monitoring and queuing and sampling ports. Because of this, many of the ARINC 653 capabilities are available for use by personalities outside of the ARINC 653 environment. Our Apex personality, therefore, implements the standard Apex API layer on top of this functionality. Moving on, PikeOS also supports a POSIX environment based on a subset of the PSE52 profile. This is complemented by a number of real-time and PikeOS extensions, like support for the ARINC 653 style ports, as I mentioned previously. Our POSIX personality can be used for application development from day one, but also provides an easier migration path for applications originally designed for Linux. As PikeOS boasts performant hypervisor support, this opens the door to support a number of guest environments, including fully fledged operating systems like Windows, Android, and Linux, for example. So, a major consideration in the design of multi-core systems is how resources are safely and securely separated. Let's touch on the technologies in PikeOS that offer support for this. PikeOS uses multiple methods to ensure strict separation of applications within the OS, facilitating the development of deterministic, mixed criticality, real-time systems. Temporal separation is achieved through time partitioning, which is configured statically at build time. The diagram shows an example time partitioning regime whereby each partition is given a single time window. To expand on this, PikeOS implements a priority-based preemptive scheduler. So if time partitioning isn't used, a pure priority-based preemptive approach is taken based on a static priority attribute assigned to each partition. When used alongside time partitioning, the context of the priority is kept within the time window. Since PikeOS supports multi-core Intel CPUs, this time partitioning can be used to configure flexible partition-to-core schemes. For example, partition core affinity can be configured such that a partition can be granted full and exclusive access to a single core each. Equally, a partition can be granted an exclusive time window across all cores, known as partition time window affinity. In reality, more complex configurations are possible as long as there's a common major time frame between all calls. It's also possible to define multiple scheduling schemes that can be switched between at runtime using the PikeOS API. To complement time partitioning then, PikeOS implements resource partitioning through spatial separation. The separation kernel architecture is designed to create strict partitioning of system resources, ensuring that applications have guaranteed access to assigned resources only. This means that applications within each partition cannot access the resources of other partitions unless it's been configured so. This also means that it's not possible for errors to propagate from one partition to another. This separation also exists between the application and kernel execution, since applications are only executed in the user space. Finally, PikeOS includes mechanisms to follow AMC 2193 guidance. Below are examples of some of the risks and mitigations. For example, cache access contention can be mitigated through the division of cache, also often referred to as cache coloring. Mechanisms also exist in modern SoCs to handle this division of cache in hardware. Memory access contention can be mitigated through bandwidth monitoring and rate limiting. The risk of interrupt overload can be reduced by using time partitioning on interrupt-driven drivers. Scheduler contention risk is managed by using the scheduling mechanisms discussed previously, and IPC contention is not a concern if queuing and sampling ports are used, since they don't impact partitions not participating in the communication. So, how does this all tie in? Let's look at how PikeOS interacts with Intel's latest generation of safety-certifiable CPUs, the Raptor Lake. As a reminder, Raptor Lake CPUs contain both performance cores and efficiency cores. PikeOS sees all cores as a single multi-core processor, therefore spatial and temporal separation works transparently. Efficiency cores can be utilized for high-integrity applications through the use of the configurable hardware lockstep. These lockstep cores appear transparently to the PikeOS kernel, so there's no special configuration required to utilize them. Since processors in lockstep run the same instructions in parallel, there is a level of fault tolerance and detection integrated into the hardware already. And of course, the performance cores can also support safety-critical applications alongside the development of software-based mechanisms to ensure integrity of the application. Finally, compared to previous Intel CPUs, the safety island has been developed for Raptor Lake as a component external to the CPU. This greatly eases software development and integration, since this safety island no longer relies on technologies ported onto the OS. This also means there's a reduction in effort from a DO178C perspective. When combined with DAL A certifiable processor boards from Curtiss-Wright, the combination of operating system and CPU realizes a highly certifiable and capable platform available to developers now. This platform not only represents the productized approach, but also demonstrates the joint collaboration between SYSGO, Intel, and Curtiss-Wright in the avionics market. Of course, this ecosystem is extensible based on the use case as we work with established partners like Wolf SSL, Core AVI, Lauterbach, and many more. There's a full list of SYSGO partners on our website.
On behalf of myself and the team, thank you for your time today. If you have any additional questions or would like to talk to us further, here's how you can get in contact with us, and we look forward to speaking to you further. Have a great one. Thank you. Bye-bye.